Okay, so it's Tuesday, October 10th. This is the day that we had the class clash. So many people in fourth period didn't get this full lesson. I would encourage you to look at this particular link, which should be on your worksheet. Everybody who reported to class did receive worksheets. I also would encourage you to kind of recall the demo that we did. We took two different powders and we put them into a plastic bag. The first powder looked kind of like table salt. It wasn't really a powder, I suppose. It was white. It looked like table salt. You put it into the plastic bag. The plastic bag got cold. The second one looked more like dipping dots, if you will. And that one, it got hot. So first thing we're going to do is we're going to look at the equations for those two demos. So this would go in to the bottom of your worksheet. I'm going to encourage you to pause right about here and make sure that you have copied down this particular set of information that's here regarding some symbols that you sometimes see in equations, because we are going to need those. All right, so for demo number 1, this was the equation. Remember, the first one is the word equation. The second one is the chemical equation. Pause here and go ahead and write those out. So now that you're done pausing, let's talk about a couple of things. One, that this S means solid. These AQs mean that it's dissolved in water. Notice that heat is a reactant. It is on the, what is this, left side. I would never expect you to know these symbols. I wouldn't even expect you to know these names unless they were given to you in a sentence. All right, next deal is the demo number 2. This is the one that got hot, the one that looked like dipping dots. Take a moment and pause. In the process of pausing, I realized I left out something very important, and it's that both of these reactions have heat here on the product side. You can see the S for solid and the AQs for aqueous, which simply means that it was dissolved in water. So from here, I want to talk about a couple of different things. First and foremost, let's talk about systems. So on the next page of your package, you have some important words. You'll want to use Discovery Education to describe these words, or define rather these words, and know those definitions. Heat is the transfer of thermal energy, and it's actually very different from temperature, which is average kinetic energy. Kinetic energy is the energy of motion, and typically when we're looking at the kinetic energy or the temperature of something, we're focusing on the system. The surroundings is everything but the system. So in the case of a plastic water bottle, the system is the water inside the bottle, and the surroundings is all of the air outside of it. In the case of a spaceship, the system is the spaceship and all the people inside it, all of the materials that are inside it, and the surroundings is everything else, so the universe. We also need to talk about a couple of different types of systems that we'll talk about. One is an open system. So imagine that water bottle that you've taken the top off of it. If you take the top off that water bottle, matter can come in and out, so you could spill some water, and heat can come in and out. In a closed system, there's a lid on it, and so that nothing can come out of it. Nothing means matter, but heat can still come through it. An isolated system is one that is theoretical. It doesn't actually happen, but we strive for that. In engineering design, it's one of the goals is to wind up with an isolated system, one that neither heat nor matter can get through. So let's define a couple of different reactions. We have an endothermic reaction. So an endothermic reaction is one that requires heat to go inside it. If it's a chemical change, it tends to feel cold because it is literally stealing heat from your hand in order to get the reaction to go. Because it is stealing heat to make the reaction go, heat is a reactant. And a good example of this in terms of physical changes is melting water. Now that's counterintuitive because you would think that melting water would be an exothermic process, but actually melting water is an endothermic process because it requires heat to happen. Heat has to go inside in order for it to happen. Another one of these that is endothermic, that feels counterintuitive that it is endothermic, is condensation. So when something cools down at night and you wind up with dew on your car. All right, exothermic. The prefix exo comes from the Greek word meaning outside. The chemical changes themselves feel hot. You'll feel a lot of heat coming from them, and heat is a product of these reactions. Freezing water to make ice is actually an exothermic reaction because you need heat to leave the water in order to freeze it. Another good example of an exothermic reaction is sweating. Sweating is an exothermic reaction, and that's why we feel cool when it happens. We, the person, feels cool because from our perspective, our heat is being taken away from us. So that is how sweating works. So we have endothermic reactions and exothermic reactions. Endothermic reactions require heat in order to go. They have heat as a reactant and they feel cold. Exothermic reactions give off heat when it's a chemical reaction, and they typically feel hot when they happen. So what I would like you to do is to take the information that you have learned and apply it to this particular picture. This is the picture that had the beaker at the top. I'd like you to draw some arrows into or out of this closed system to tell me where heat is going. Actually, it's an open system because the beaker is open, but all I really want to know about is heat. So if we had a reaction happening inside, let's say this is our reaction here, which way would heat go? Would heat go in or would heat go out of the reaction? So I'd like you to label the two beakers. I'd also like you to give me some reactions. So what might you see? Is an endothermic reaction one that you would see the condensation on the outside? Is it one that you would see sparks? Is it one that you would see steam come off of it? And the same thing for exothermic reactions. I would like you to tell me about their equation, and I don't want you necessarily to write the equation. I want you to tell me where heat is. Is heat a reactant or is heat a product? And I'd like you to give me some examples. So if you go back through your notes and perhaps use some of the Discovery Ed links that you will see posted, you will be able to do just that. Thanks so much. See you next time.